structure of tonight's presentation is pretty straightforward. I'm going to talk about the problem that we had, the algorithm that was chosen to solve to implement the solution, but it ran too slowly. And then two different sets of solutions. The first set we did in 2011, the second set in 2012. I say we mostly because I have tapeworm. Hey, it's a transparent universe now. You can't hide anything. My doctor's pretty upset because I'm the only medical record in his office still on paper. Everything else is computerized now. I said, I know how this works. Keep me on paper. Then we'll talk about future steps, more things we could do to speed up the program. And the second half of this presentation is going to be lessons learned. I always think it's worthwhile to spend a few minutes and learn from your mistakes so you can make them again. The problem that we're faced with is fairly straightforward, a common problem in these sorts of enterprises. We sell, as I said, games. We don't really sell them. We mostly give them away for free. And our games are very fun. We have a huge pile of people at our company who know how to make things that are fun. We're an entertainment firm. It's what we do. Internally, we have a different definition of fun than just fun. We have a whole bunch of key performance indicators that tell us how fun the game is, and we tweak them to make the game more and more fun. Or we measure them as we tweak the game to make it more fun. To figure out how to tweak the games, we ask hundreds of questions across all of our games. And to get the small signal from the large amount of noise, we have to collect huge amounts of data. The data is collected from our servers on how our guests are playing the games. We don't collect any invasive data on the user's computer. We just collect data on the server end. For each of these hundreds of questions, we're going to take all of this giant data set we have and create 500 synthetic variations of that data, and then do a particular computation that I still don't understand. And the result of that is the answer to the question. We have hundreds of millions of rows. So this is a classic big data problem. I feel a little bit goofy using the word classic to describe something that's only a couple of years old, the concept of big data. But technology moves quickly. Beginning of last year, we had a prototype written by our chief analyst, who is very good with statistics, not so great with programming. That's OK. I can't do the analyst job either. When I learned statistics in college, we were using Roman numerals. Try doing square roots in Roman numerals. The best language for that, by the way, is Intercal. If you haven't played with Intercal, this is a great time to learn it. Kind of. So the program worked correctly, but for just a subset of the processing, it took far longer than the batch window we had available. The best case batch window is 4.5 hours. It's frequently less than that. So obviously, we needed a better solution. And this graph stops in March of this year, because as I said, I like to keep my job. But you can see we have more and more data coming into this program. So we have more questions being asked. For each question, the answer to that question is recomputed every night from all of the data ever collected. Not a very good idea. We're fetching all of the data every single night. And the amount of data is increasing as well. So we have a problem. You can see where the problems lie. This is the guts of the algorithm. By the way, if you're wondering why I keep stopping, I'm not doing William Shatner. It's just I have no idea what I'm talking about. Not every joke is a winner. Some are good, some are bad. So this is the basic algorithm. This looks like Python. It's really pseudocode. After I wrote the program, I went back and did the pseudocode just for these slides. And the code you see here in red is the outer loop for each of the jobs. So phase 1 in white at the top, we get the list of jobs. I'm sorry, that's phase 0, get the list of jobs. Phases 1, 2, and 3 are inside the red loop. Phase 1 is the next 2 white rows. Talk to the database to get the data and convert it into NumPy. Then phase 2 is the blue loop, and that's analyze the data. And phase 3 are these 2 lines here at the bottom where we write the results back to the database. Not terribly complicated. The blue loop there for IN range 500, that's where we're going to do these 500 random resamples of the incoming data. Those resamples are the same size as the original data set and consist of the same data from that data set, but the rows are selected at random. So some rows might appear multiple times in the synthetic data, and some rows might not appear at all. In the inner loop, we're going to take the random indices that we create with the white line just above the yellow line. We use those indices to create the synthetic data from the original data. And then we're going to do 2 sets of sums over all the rows. In the first sum, we're going to sum up those rows where some condition is true. And in the second sum, we're going to sum up all the rows where the condition is false. The result of that is 2 arrays, sums t and sums f. We pass those into some functions that generate SQL and write a couple of rows into an output table. Again, not terribly complicated. You may be looking at this and thinking a couple of questions. Well, you may be thinking, first off, why not just run it on Hadoop? That's a good question. I'm going to come back to that later in some depth near the end of the presentation. And you might also be looking at this and saying, this is horrible, inefficient code. Well, yeah, when you start with horrible code, you can get major speedups. That actually was not a joke. We don't do a lot of performance tuning anymore. Programmers are pushed to get features and functionality out the door and not to take time to make the code fast. There's another way to make the code fast called scalability. And in the second half of this presentation, I'm going to talk about why scalability and Hadoop are crippling our ability to provide services to our customers. Here's that same algorithm where I'm just calling out what's going on. Phases 0, 1, and 3 are just waiting on the database. Phase 2, where we're actually doing the analysis, is doing lots and lots of random reads from the original data, sequential writes to the new data, and then a couple of passes to compute the where clauses and the sums. So it's not too hard to look at this code and figure out where the time is probably spent. What I'm going to do now is describe the speedups that were done. First, we're going to look at the speedups in 2011, and then the speedups in 2012. I had 8 weeks of time in 2011, March, April, and May, with a hard stop in May because I go to New York and see all the shows I can, and then I take my mom to one of them so I can justify ignoring her for the rest of the year. I grew up in New England. We didn't get kissed goodnight. Mom would wave from the other end of the room with the back of her hand. The first of those speedups is hoisting invariant code. I spent 2 weeks of the 8 weeks just cleaning up the code. It went from 700 lines to 2,000 lines in the process. But the resulting code was well structured. Duplicate facts were centralized. Magic numbers were given names. In several cases, there were magic numbers where the same number would appear in multiple places with different meanings. So I had to figure that out, back that out of the code. There was a lot of invariant code inside loops to pull out. Python can't do a lot of these optimizations. The language is too dynamic to figure out at compile time what it can safely do at runtime. So I had to do a lot of stuff to address the fact that Python really can't optimize terribly well. I noticed in the process that in here, in this where clause that I'm not going into any detail on, there were some numbers being computed, 4 numbers being computed for every row, every time, and they didn't change on the various iterations of this loop. So I hoisted all that stuff out. In the database query here, where we get the data for a given question, job and question are synonymous in this case, we have 17 columns coming back from the database. I took the 4 numbers and added them. So instead of 17 columns, we now had 21 columns. Pre-computing helped quite a bit, gave us a nice speed up. Next speed up that I did was pipeline parallelism. Lots of ways of doing parallelism. Pipeline parallelism is a fairly simple approach. You take a problem and you break it into pieces and you run all those pieces in parallel. So instead of running them sequentially, you can now run them simultaneously in time, vertically in time. So I took the program and I split into the fetcher program, phases 0 and 1. Get the list of jobs is phase 0, and then for each job, get the data for it. That's the fetcher. The fetcher does that work. It's kicked off when our batch job tells it that the prerequisites have been met. And for each job, it writes the data for that job, millions and millions of rows, into a little file. The next process, the analyzer, is only running the CPU-intensive part of the code. That's this part here, the stuff roughly in blue, the blue loop. The analyzer is running continuously. We have not turned it off in well over a year. And it just monitors the directory where the fetcher writes. When it sees data has shown up, it reads the data, processes it, and erases it. Very simple. It writes its results into another directory, and in that directory, the third program, the writer, is waiting. When it sees results to be written, it writes them out. So it's looking for the results of this calculation. When it sees them, it writes them into the database. The writer runs very, very quickly. It's only inserting a couple of rows. The fetcher and the analyzer were originally taking about the same amount of time. So by running them in parallel, I doubled the speed of the system. That's nice. That doesn't happen too often, but it's nice when it does. However, over time, that benefit grew less and less because the analyzer quickly became a huge bottleneck. Once I started doing the full processing and not the subset that had been in the prototype. So when you have one phase of your pipeline taking a lot longer than the rest, the benefits of overlapping the processing go away. And then later on, with the work I did this year, the analyzer started running so quickly that it took far less time than the fetcher. Again, we weren't getting much benefit from overlap processing. However, when I did the restructuring, I also set it up so that I could rerun any point in the pipeline very quickly. I could rerun my standard test cases, and by having 3 separate programs, I could run just one of those programs more quickly than running all the entire code together. So I had quicker reruns, and I had simpler programs. It's easier to deal with figuring out what's going on with a block of code you don't understand when there's less of it. Pipeline parallelism is one simple way to get performance, easy to implement. You have a producer and a consumer, pretty simple relationship between them. I also made a fix to NumPy. The result set coming back from the database in phase 1 here had 17 columns, a mixture of floats, ints, and one string. When we pass that result set into NumPy and say, hey, NumPy, make a NumPy array out of this, NumPy does what we tell it to do, but NumPy in the naive form requires that all the elements in the NumPy array be the same type. And what's the least generic type to represent int, float, and string? PyObject. Which means that later on when we ask NumPy to do high-speed numeric calculations, it really can't. It has to call back into Python for every single element to get the current value. So I fixed that. I replaced that one string column with an integer lookup table, an integer value. And I found out in the process there were only a couple of unique values in the string because it was really a version number. So this provided a nice speed up, but at the end of last year it was made obsolete when they changed the database table to replace that string column with an integer column as it should be. I'm not arguing, that's a fine thing to do, it simplified the code. But it was quite an improvement because now NumPy was actually providing high-speed numerics. It converted everything into float, the least generic type that can represent int and float accurately, reasonably accurately. One more speed up that I did last year, the multiprocessing module. Instead of doing all of the work in the analyzer in one thread, which is the way the code was written before, I parallelized it to run in many threads. The first time I did this, I spawned one process for each of the 500 loops, and of course the computer fell over and died immediately. And I realized that for CPU-intensive work, that's kind of silly anyway. If you're doing CPU-intensive work, you only need as many processes as there are cores. No point in having more. Just be wasting time in context switching. I used fork without exec. How many people here are familiar with fork and exec? I hope to see a few hands go up. For those of you who aren't, fork means make a child of my process that is an exact image of this process, byte for byte identical, the same open files, everything is the same. They can tell which one is parent and which is child by basically the process ID, and that's about it. The nice thing is that in modern Unix systems, anything after the mid-80s, fork is very low cost because we don't actually copy the address space, we just copy some page table entries. And in the present case, that means that all the children processes were sharing this data, which is read-only. After a fork, if the parent or child make changes to pages, they get a private copy. But since neither parent or child is making a change to that NumPy array, there's no copies being made. The result is I got a near linear speedup. The startup overhead, the serial part of the code is very small. The parallel part is very large, so we get a near linear speedup. Amdahl's law works in our favor in this case. Here's what the analyzer looked like. Again, this is pseudocode that looks like Python. That's the great thing about Python, isn't it? You write pseudocode, and then 5 minutes later you have a functioning program. It's just Python. So this is pseudocode that looks like Python and almost is for just the analyzer part. The analyzer has, at this point in the code, figured out that there is some new data to analyze. At the top of the page there, the top of the screen, it reads in that data. The data has been already converted by the fetcher into a NumPy format, so we can simply suck it right in and go. Then I have middle loop number 1. I create all of the parallel processes and I start them running. I'm using the multiprocessing package, which is part of Python. Python has 3 ways of doing parallel processing easily. It has multiprocessing, it has threading, and what's the other one? Subprocess, I think. And then, of course, you can use pipes and stuff and OS calls to do multiprocessing in other ways as well. Multiprocessing is great because it just uses fork. When each process is started, that first of the blue lines there, the new process, the child process, is going to execute compute wrapper, which has passed in the data that was read in from the data file. And now instead of running 500 loops in blue, we're going to run 500 divided by the number of cores, because we have number of cores processes running in parallel. And we do our calculation, and we get a nice speed up. In 2011, when I did this, I was operating under the belief that hyperthreading wasn't terribly useful. So I limited the number of cores to the number of real cores, not hyperthreaded cores. Later on this year, I tried jacking up the number of cores the program used until I used all the hyperthreaded cores. And it actually ran faster and faster the more hyperthreaded cores I gave it. So that was an unexpected benefit. One little fly in the ointment. The join call here is where we wait for all the children to die. This is a model I'm familiar with in my religious tradition. That's basically what parents do. They wait for their children to die. And if you think about how that's going to work, that's going to operate sequentially because it's a list comprehension. It's going to start at the beginning and go all the way through to the end. So what happens if the first process happens to take a long time and all the subsequent processes finish very quickly? Well, in that case, we're just wasting time. All the other cores have nothing to do. We don't have any more work for them. So this is an example of statically scheduled parallelism. Insanely easy to write, 3 lines of code, but you do have a speed bump. In this case, it's not too bad because each of the children take about the same amount of time to run because they all do about the same amount of work. That was the theory. In practice, I saw that actually there was about a factor of 2 variation in the runtime between the child processes, and I wasn't happy, but I'm also very lazy, so I didn't fix it. Well, lazy, but then again, good enough is perfect. When you get to the point where your program is fast enough, you're finished. Move on. There are other things we need to worry about. It is easy to fall into a rut of performance tuning forever and never actually ship anything. I've worked at those companies. This went fine for the rest of 2011. In early 2012, we had a problem. This program had proven to be very, very popular. So there were more and more questions being submitted to it. And remember, every time the program runs, we recollect all of the data from the beginning of time. So the data gets bigger and bigger every day. Combine those 2 factors together, and you have a problem in size. In addition, management decided they wanted to do more sophisticated analyses. We haven't actually done that, but had that occurred, we would need another factor of 10 or so in performance. The situation had gotten bad enough that by February, the fetcher alone was taking more than 24 hours to run. Clearly wasn't going to finish in the batch window, wouldn't even finish in the day, so we needed more speed. First thing I did this year was take the program, the analyzer, because it's the CPU-bound part, and run it on a machine with way more cores. Obviously, that will speed it up. How could it not? And it didn't. And I was vexed. I was wroth. I was ired. I was concerned. I was puzzled. I went through all 7 stages of grief. It took a week. For 1 solid week, I ignored what the data was telling me and stuck with my own preconceptions. We just concluded a presidential campaign in which one side did that to their numbers, and they didn't get the results they were expecting, did they? There's a lesson there. We'll talk about that later. But if elected, I will not serve. So you have to be of a certain age to get why that joke is almost funny. So after a week, I said, OK, if it's not CPU bound and it's not IO bound, what could it possibly be? And I had a stroke of lightning, or possibly just a stroke, that perhaps it was memory bound and not CPU bound. Well, how can I take that hunch and convert it into a theory? How can I test it? Because if you can't test something, then you don't have a theory. What I did was I took that NumPy array, the 21 columns of 4 bytes each, and I split it into 3 arrays. One array had the columns that really needed to be floats. The second array had the columns that could perfectly be 2-byte ints. And the third array had columns that could just be single bytes. Most of them, in fact, were just bits. Very easy to do that kind of re-screwing around with your data in Python. You don't have to worry about going into a header file and messing around with headers. You don't have to fight with your Java compiler nonstop. You just do it and it works. Don't get me wrong, I love Java. It's a great language for bad programmers. But if you're competent, you can use Python and get better results faster. Again, that was not a joke. But I'll take the laugh. And the program sped up by the ratio of 84 to 36. Big, huge, huge, giant clue. So at that point, I went all out for reducing memory bandwidth. I used a radix sort to take the array of random numbers, which are indices into the main data set that we're going to use to copy that data into the temporary data set. I took that random array and I bin sorted it, I radix sorted it. I love radix sort. I came up with this in college and then figured out, of course, somebody else had invented it 100 years ago. But it wasn't until Wikipedia that I was able to find out what it's called. And if you don't believe me, wait until 5 minutes after this is over. Give me a chance to get on Wikipedia, and it will be there. The result of the radix sort is an array the same length as the number of rows in the original data set, and each entry tells me how many times the corresponding row should appear in the synthetic data set. So if the first entry in the bin count array, the result of the radix sort, has the value 10, it says that row 0 should be used 10 times. And if the second entry has the value 0, it says row 1 should not appear at all. Once I have the bin count array out from radix sort, I now have a virtual synthetic data set. I don't need to actually copy the original data into the new data. I can just use the radix sort to pretend that I did that. So I've now eliminated one entire set of random reads from the original data and one set of sequential writes into the synthetic data set, because I don't need to actually create it. This takes advantage of the fact that row order is unimportant in our algorithm. All we're doing is summing up rows. The order of summation does not work. It does not matter, because addition is commutative. I was expecting a laugh there. OK, we'll just move on. I guess not everyone went through new math in junior high school. Good for you. Didn't work. Made me the man I am today, a man who hopes to someday afford long pants. So here's the basic change. We take our random array, and instead of just using it, we pass it to the radix sort, and we get back our bin counts. And we get all this nice stuff. Also, inside the inner loop, I had that where clause. I got rid of that as well. So that got rid of more passes over the data. Next thing I found was that because the user time had been reduced so much via that change, the system time was now significant. System time didn't go up any, it's just that user time went down a lot. And I profiled the code, where's the system time going? It turns out that those random number generator calls are expensive. Remember, we're calling the random number generator for every single row times 500 iterations. And we have millions of rows times 500 iterations, that's a lot of calls. So I changed the code. Instead of 500 times the length of data, I made it 500 plus the length of data. Here's what I did. Generate that list of random numbers, but just generate one list, not 500 of them. Create the bin counts, as we said on the previous slide. Now take the bin count array and append a copy of it right to the bottom. Make a list of 500 more random ints between 0 and the number of rows. We're going to use those to index into this double bin count array at any random location, and since it's twice as long, we know that we can't run off the end no matter where we start. The result is not as random as if we did 500 times the length of data, but random enough, according to both the analyst who looked at it, and also running the code and getting the same results. Again, good enough is perfect. Let's move on. We're not physicists who want the correct answer. We're engineers who want an answer that's good enough. The word engineer comes from the same Italian root as ingenious. Ingegnere is what I was taught in college. It's a Renaissance word. We are ingenious. We don't need the right answer. We need one that's good enough. At the other extreme, we could be artists or accountants, where it's, what answer would you like? I'm flexible. Those of you who laughed will be audited, just so you know. Next thing I did was touch the big data only once. This is a little bit tricky. I realized that the original algorithm, 500 passes over the original data, means we're going to be flushing all the caches in the system 500 times as we swamp them with the huge data sets coming through. Not a good move. We don't want to do that, so I swapped the inner loop and the middle loop. Now the middle loop is going to go across all the rows, and the inner loop is going to do the 500 iterations. This slide is oversimplified because remember, it's not 500 anymore. It's 500 divided by the number of cores due to parallelism. But to make things fit on the slide, I'm just leaving the number 500 there. So on the inner loop, each time around, we choose a new starting location in the bin count array. That was the speed up I talked about before. And we have some much simpler code here now. This code turns out to be an improvement because we're only going over the big data set once. Big improvement. Remember, this program is memory bound. Anything we can do to cut down memory accesses is a win. I'm not going to go over this in detail. If you really care about the details, download the slides from these websites. Feel free to send me an email later on. My email address is down there at the bottom. You might wonder why I'm using HTTPS for my personal website. It's because I upgraded the firmware in my router yesterday, and now HTTP doesn't work anymore. Thank you, Linksys, once again. Notice that this line down here is really doing a vector times a scalar and adding the result into a vector. Python really isn't set up to do that. I don't think you can even express it with NumPy. Maybe you can. I might be wrong. But what's really happening there is an inner loop because we're going to have to iterate across each of the elements in the current row to do that. So that's an inner loop. But there are only a few elements in the row. Remember I said there were 21 elements, and we're only summing up 16 of them as it turns out. So the cost of that inner loop is pretty trivial. But we could unroll it, and in a moment you're going to see that exactly. Next thing I did was I contracted with some folks at Continuum Analytics in Austin. I met them at PyCon earlier this year. What a wonderful conference that was. That was probably the most useful conference I've ever been to. SIGGRAPH has got more eye candy, but PyCon was terrific. I got the hat. I got the jacket. I went to all the tutorials on performance, most of which were good. And I met these nice people from Austin, Continuum Analytics. I also got a chance to go out to Austin, a wonderful city. I'm not sure what it's doing in Texas, but it's a great city anyway. They helped me figure out how to use Cython. For those of you who aren't familiar with Cython, it's a program that takes Python code that has had type annotations added to it and generates C code from that. Plain vanilla Python gets its flexibility because it uses late binding as much as possible, the latest possible binding. That makes Python flexible but incredibly slow. Cython does the reverse. Cython converts Python into C code where all the bindings are done as early as possible at compile time so that you do as little as possible at runtime. A huge performance benefit, but you give up flexibility. The result of Cython on just my roughly 40-line compute kernel in Python was a 6,000-line file of C code. Most of that was boilerplate. I found out the parts that were the actual variable code, and I hand optimized them. It ended up being, after getting rid of a bunch of CRUD, 62 lines of C code. 62 lines of C code. That's reasonable to get a huge speed up, which is what I got out of this. And this is the beginning part of that. I'm sorry, this is the inside loop. At this point in the code, we have selected one row to process, and we are on one of the 500 iterations. And we have figured out what the current random value is corresponding to that row. That is, how many times should that row appear in the synthetic data set. And there are only three choices for the count. Either it's 0, which means this row shouldn't be used at all. And that's the line at the top there. If v bin count is 0, continue. Or the value is 1, or the value is more than 1. I distinguish between those last two cases because if it's 1, I can add the current row to the current accumulators. And if it's more than 1, I have to do a multiplication as well as an addition. And you can see that, let's see, this block of code here is all about choosing the appropriate set of accumulators. Remember, we're doing all 500 iterations in parallel at this point, so I have to choose one of 500 sets of sums t and sums f. And then I have to choose if it's sums t or sums f. So that work is being done here. Again, I'm not going to go into great detail on this. You can download the slides at your leisure. And down here, I do something which is not C code and is not in the actual file, but I made it look like this so it would fit on the slide. I'm taking the current count, multiplying it by all the fields, and adding them to the accumulator. If the count is not equal to 1, I do that. If the count is equal to 1, then I just take the fields and add them. So it looks like that on the slide to make it fit, but if we go to the next slide, you can see what the code really looks like. At the top there, you see if v bin count is 1, just do an addition. Otherwise, do a multiplication and an addition. This is not rocket science. This is not the sort of code that should make you, I don't know, mess your pants. Good, I was afraid I'd get a laugh at that, and I didn't want to laugh at that. Scatological humor is not my type of thing. There is something a little strange going on here. If you can read this code, I don't know if you're past the third row, you probably can't even see the slide terribly well. I'm not adding up the columns of the current row in order. I'm adding them up out of order. Now, the first version of this code, straight out of Cython, did add up the columns in order. So take the first column, add it to the first accumulator, the second column, add it to the second accumulator, and so on. And I had a thought. It happens occasionally. Happens especially if you are obsessive and can't stop thinking about this stuff. Please put down the computer and come to bed. Oh, just one more minute. Really, I'm almost done. 3 hours later, please put down the computer. Go. If you wait long enough, they go to sleep on their own, and that's much better. My thought was that in that obvious structure of adding up the columns in order, the first addition is going to go to some line in the L1 cache to pick out the current value of the first item in the row. And then it's going to go to some other location in the L1 cache to pick out the corresponding accumulator, add the two together and write them back into that line in the L1 cache. Then it's going to want to add the second column to the second accumulator, and that's going to touch the same lines in the L1 cache because they're probably right next to each other. There's no other place they would be. And then we're going to move on to the next column and probably hit the same cache lines again. How many times can you do that on a modern system? I don't know. But I do know that the computer inside is not behaving like we were taught back in college. What we were taught was that the computer executes instructions in order, and that those instructions are executed against a simple flat address space where the location of all, where the access time to all locations in memory is identical. And that's not what really happens on these machines. What's really going on inside is that the computer is aggressively looking for runtime parallelism in the instruction stream and using that to run instructions in parallel. So if I give it a little bit of help, then it can run these additions in parallel, and that's why I permuted the order here. So I do the first item in the row, sums p sub 0 plus equal v fields arrow a1, and then I skip ahead to the fifth item, index 4, because that way, when the computer is trying to get runtime parallelism from the instructions, it will say, oh, these instructions don't touch the same cache line. I can run them in parallel. Factor of 2 speed up. To do that required somebody with a fairly general background, and that's my background. I'm a generalist. That's a polite way of saying dilettante, which means I don't know squat about anything. But I know a very little bit about a whole lot of stuff. Most of the folks in the audience tonight are probably specialists. That is to say, you're probably really good at something. Hold on just one second. You shouldn't need to know this level of detail. You shouldn't need to know about out-of-order execution and multi-level caches to get this kind of performance. And that's going to be much of the focus of the second half of my talk. Yes, sir?
So how did you know that you need to advance by 5 to make that possible?
Advance by 4, I hope, unless I screwed up the slides. The cache line is probably 32 bytes wide. Okay. If you check the spec sheet, it says 32 bytes wide. I have 8-byte floats at this point in the algorithm. so I can fit 4 of them in a cache line.
I see.
Hold on just a second. That's an example of false sharing. And again, I shouldn't need to know this stuff, but I had to get the speed. Yes, sir?
So that means your algorithm is architecture specific.
It certainly is. If you want to get the highest performance, you have to know what's the machine you're running on. Python makes that impossible. We're too far from the machine. Java, PHP, Perl, they're all wonderfully productive languages, but they take us so far from the machine that we can't make intelligent decisions. And even if we could, we can't tell the language what we need to do. So you got to drop down into C to do this low-level stuff.
Doesn't the compiler usually take care of this automatically?
I don't know if compilers are smart enough to do this. Certainly when I looked at the assembly code coming out of GCC, it wasn't doing this. And I was asking for all the optimizations it could give me. It would be lovely if it could. And I'm going to talk a little bit more about that near the end, I think the last slide of the entire show. Kind of speaks for itself, doesn't it? This is back in 2008. I talked to some folks at Twitter, sitting across the table. I asked the guy, now, your stuff is written in what? And he says, oh, we use a LAMP stack. It's wonderful. It's the way to do things. Okay. What exactly are you doing? Well, we're routing 140 bytes from your phone to somebody else's phone. Okay. Why are you doing that with a LAMP stack? Well, it's the way things are done. I have a hammer, therefore this thing must be a nail. I can pound on it. And in San Francisco, you can get away with slaughtering meter maids. No jury will convict you for that. But you can't kill programmers. I did want to ask the guy, have you ever called outside 415? That is a long-distance phone call. What do you think the phone switch is written in? It's either C or Erlang. If it's from Ericsson, it's probably Erlang. Or have you ever flown on an airplane that wasn't military? If it was a commercial jet, the avionics is probably written in C. Use the right tool for the job. Don't get tied down to one language. Python is a great language. I've been programming in Python for 10 years, maybe 11, depending on how you count. If you're a physicist, it's 10. If you're an engineer, it's 11. Close enough. 11. I love Python. You will not find a stronger advocate in Python. Every company I've been at for probably the last 5 or 6 years, I have been the strongest Python advocate. But just because it's a great tool doesn't mean it's the only tool. When I had a carpenter in remodeling my condos, he had 5 hammers in his toolbox, and he could explain to me each one. And he said, you really want to know? I said, yes. He said, I'm charging you $200 an hour. I said, $200 an hour? I'm a programmer. I don't get $200 an hour. He said, yeah, when I was a programmer, I couldn't get that kind of cash either. But he had 5 hammers. Each one did one job very well. The same is true of computer languages. Use the right language. Don't get fixed on a particular language. There's some more things we could do to get more speed, because to get to that 114,000 I promised you, I would have had to do more than what I did. I stopped when I got a total of about 12,000 because that was good enough. And I'm going to tell you why that's the case in a moment. But here are things I could do to get to that 114. And how do I know it's 114? Because I did read the specs. As you were asking, it's architecture specific. I went into great detail on what microprocessors were in these cheap-ass servers that our crummy provider gives us. And I know how fast the machine can do computation. So I was still off by a factor of 10 at least. And there's no reason we should not be able to extract all of that performance, because what's this algorithm doing? It's adding numbers. What are computers good at? Adding numbers. So here's some things we could do. First item, use faster hardware. In the old days, we called it a forklift upgrade in the mainframe days. But nowadays, it's not a forklift. A server is this big. And we're not even going to take the old server out. We're going to make it a dev box. So just use faster hardware. The problem goes away. We can move on to something new. We don't even have to get involved. We can let our ops team do that. Life is grand. We can go see Skyfall. Tip of the day. It's not a very good movie. It's a great thing about working at an entertainment company. I can actually go to the movies and say, I'm working now. I'm not going to point at my coworkers, but you know who you are. I did not do that. But it really is not a very good movie. Those bit-valued columns, those byte columns are actually bits. You could combine them all into a single byte and then pull that data out later. That would cut your row width from 36 to 30 bytes. I actually tried that on some early versions, and it slowed things down, which is surprising because the cost of pulling the bits out is just a single and that should have been hidden. That should be zero cost. It wasn't. It would be interesting to try that again with the current version of the code. More interesting, because it's a shiny toy and I like shiny things, would be item 3, use the vector instructions. So every L1 fetch would not give us 1 operand, it would give us 4. Or if we use some of the other more advanced vector instructions, I think you can pull 8 out at a time. I'm not quite sure how the hardware does that. But anyway, we should be able to get a huge performance benefit because we could do the work in vector mode. Big improvement. Also, the latter half of that slide that had the unrolled C loops on it, where I was doing multiply accumulate, there are special instructions for doing multiply accumulate. So instead of having to multiply bin count by each value in the row and then adding to the accumulator as separate instructions, I could do the multiply and the addition in one instruction. The new name for that instruction set on the Intel chips is called FMA, for Fuse, Multiply, Accumulate. There are some older instruction sets that do much the same thing. Those are called MAC instructions. You might wonder why the chip vendors would implement such a weird instruction as Multiply, Accumulate. It's because that's the fundamental thing you do in signal analysis. It's the fundamental thing you do in all sorts of algorithms. But in high-level languages, whether they're as high-level as Python or as mid-level as C code, we can't really express any of these vector concepts. Standard C has no way to really talk about vectors. Python has no way to talk about vectors. We have to use extension libraries, which have some substantial limits in what kind of performance they can give us. We could rewrite the entire kernel in assembler. I have a life. I don't want to do that. And to do that means, again, to the point the gentleman in the back raised earlier, means our code would really be bound to this particular computer architecture. That's good for about 4 years. And then we'd have to think about rewriting it for some new architecture. I'm not happy doing that kind of work. It's weeks of work to write that assembler language. I'm not sure it's going to give me much benefit. I don't like the risk of taking on that much work and not knowing if we're going to get results. A couple of completely weird ideas. On multi-socket machines, each socket has local RAM and can talk to the RAM and all the other sockets over an interprocessor link. We can use Python calls that bind to the underlying Linux calls to tell Linux, make sure that all of the RAM for this core is allocated on the RAM attached to this socket, so we don't have to go over the interprocessor link to get to the data. There might be a benefit from that. There might not be. I don't know. We could also try around playing with the scheduler to use processor affinity. Maybe that's a benefit. Maybe it isn't. Easy to try. I doubt it's going to provide much benefit. Item 7 is even more weird. We could port to the GPU or to Intel's new Phi chip, referred to as LRB because the predecessor was called Larrabee. We could port to the GPU using the Python high-level library, or for even more performance, the low-level GPU primitives, which then binds you to that particular GPU architecture. That would get us a huge amount of speed, but then you got to get your data center to provision machines with GPUs. Not all data centers are willing to do that. And the code becomes kind of unpleasant to write and understand, so that might be a great way to get more speed if we needed it. The last item on the list is run this on a cluster, and my boss was all over my butt. Every couple days, run this on Hadoop, run this on Hadoop. Well, boss man, the speed up you want is this big, and our Hadoop cluster is this big. The folks at Twitter were telling me recently their Hadoop cluster is this big, which means that, never mind. Clusterizing introduces a whole new set of errors that we don't know how to deal with. We have an operations team that keeps the networking layer running and the operating system layer running, and they have tools to do that. All sorts of monitoring tools and alerting tools and predictive maintenance tools, and it's wonderful. At the apps layer, we have a team of people, that's us, who keep the applications running, and we also have tools to monitor that. Some of our tools are very good. Some of our tools suck rocks, but at least we have them. At the cluster layer, there is none of that. There is no tradition in our industry of how to manage clusters. Finding people who can do it is extremely difficult, read impossible. There are no good tools for it, and when we clusterize our code, we're introducing a new layer with a new set of failure modes that we really don't understand terribly well. And I'm going to come back to that in just a few minutes. So why didn't I do any of those things? Good enough is perfect. At this point, the analyzer was taking 5 to 10 minutes. It's still taking 5 to 10 minutes. The fetcher's taken 15 hours. So pretty clearly, speeding up the analyzer anymore was pointless. At 9 a.m., the pretty printer runs to generate reports from this. If we don't have this stuff done by 9 a.m., it doesn't really matter. Well, if the fetcher's the bottleneck, what do? We actually worked on this last week. One of my coworkers and I put in a little bit of time. The first thing we tried was static parallelism. Fetch a bunch of jobs in parallel, the same technique that you saw a few slides back, very simple to do. The problem is some fetch jobs run quickly and some run slowly. So that roadblock that I talked about with static parallelism became a big issue. Or we could have tried running it in parallel. We could run all these hundreds of fetches in parallel. I tried that last year. It crashed the database. I have worked at 3 database companies. I've consulted for a 4th. I do not understand why in 2012 we are putting up with this bullshit from databases that cannot do what they've been advertised as doing. I should not be able to crash a database by sending ordinary requests over the wire. It's okay if it sends back a failure code to say you're an idiot, stop it. But I shouldn't be able to crash it. The database we have is a commercial database. You've probably all heard the name. I'm not going to mention it here because it's such a piece of crap. I don't want to give them free publicity. It has been a disaster. Be very careful about databases. I have yet to come across one that actually does what the vendors say. One company I worked at, you would recognize their name. It's a great, big, round name. I went out with a sales guy, and he felt compelled to lie about the product, even though the product already met the customer's needs and did everything they wanted. The sales guy felt the need to inflate the numbers by a factor of 10. So he couldn't tell the difference. All right, what are other ways we could speed up the fetcher? I'm not going to go over all these, but we could load directly into NumPy. Those folks at the Continuum Analytics consulting firm I referred to, they now have a database loader that goes straight from the result set into NumPy, bypassing the needless conversion from database result set primitives to Python, and then from Python primitives back to machine primitives. We could make another attempt at speeding up the piece of crap database now that we have a dedicated resource who's an expert who used to work at the database company. I asked this person, why did you leave? And the answer was, because I can make a ton of money selling you people services for this piece of crap database. Another thing we could do, completely different idea, is instead of fetching all the data every day, cache all the previous data and just fetch the last 24 hours worth of data. Big win. We will probably do that in the not too distant future. And then an even bigger change, why are we even sticking around with batch architectures? This is 2012. It's not 1974. The first time I used an ATM, I took out 20 bucks and I went into the bank and I asked the teller, what's my balance? What do you think the balance showed? Did it show the minus 20? Not until 3 o'clock the next morning would the teller's terminals reflect the State of the Union because of batch processing. Why are we still doing this? This is insane. We're building online systems, real-time systems. Our tools should also be online in real time. The pretty printer is also a problem because the batch job was finishing after the deadline, so we fixed that by speeding up the fetcher. We now also run the pretty printer multiple times a day. In the future, we will have the analyzer or the writer trigger the pretty printer. It has a command line interface, so we can do that. And I have that code working, and then we installed a new version of the pretty printer, and they broke their command line interface. They claim it works, but they actually said in the release notes, it works, but the user interface is now completely different. Thank you so very, very much. You've broke all of our scripts. No reason why they did that, by the way. The release notes didn't say, and the enhanced value you get is blah. It's just somebody came in and changed the UI. Lessons learned. I got about 15 minutes left. Here are the topics for the remainder of the talk. The first two are about computer architecture. Well, I have to tell you my von Neumann story. I had a job as a computer technician at the Institute for Advanced Study in Princeton. It's a place where Einstein spent the last part of his career and a bunch of other smart people. I was being given a tour of the School of Natural Sciences where I was doing my technician work. And the guy giving the tour, Professor Bacall, took me up in the library and I said, isn't this where John von Neumann invented about half of modern computing? Alan Turing did the rest. And this is a gross oversimplification, but it's okay. And Professor Bacall said, yeah, he did his work here. I said, shouldn't there be a memorial? And Bacall pointed to the other end of the library. He said, yeah, over there. So I go and I take a look, and behind the bookcase is a little plaque. I said, why are you hiding the plaque? And Bacall looked at me and he said, von Neumann's work had practical applications. I'm also going to talk about scalability, why it is generally not the way to get programs to run fast, and why I believe we are being led down the garden path with the best of intentions towards scalability, and it is killing us as an industry. I'm going to beat on batch jobs a little bit more, partly because they're stupid and partly because I have a really good slide. And sharp tools for cutting is going to be the launch pad to the last slide. So let's talk a little bit about computer architecture. This is what we were taught in college. Here's the memory hierarchy. It ends with disk and tape. That's not the way computers have worked since the 1980s for microprocessors, the 1970s for mini computers, and the 1960s for mainframes. So that was a lie when you were taught it. It was never true for anybody in this room, unless you are really, really old. This is the real architecture. I've taken off the bottom two layers, disk and tape. This is what's really going on in terms of memory hierarchy. The second item from the top, physical registers, that's there to allow the microprocessor to do that aggressive extraction of parallelism from the instruction stream at runtime. It allows instructions to be executed out of order. It allows instructions to go both ways down a branch even before we know which way the branch is going to go, and then throw out the path that should not have been taken. It allows us to implement hyperthreading. It's wonderful. Everything else below that is for hiding memory latency. And that's kind of interesting. I was wondering, why is latency such a big deal? So I looked at the experience I've had programming computers, not for 30 years, but actually coming up on 40. Thank you so much. If you want to feel old, go to the Computer History Museum in Mountain View, and you'll feel fine until the last 5 minutes when they bring you up to the current day. And you look at some antique computer and say, well, that was the one I learned on. Oh, crap, I feel old. When I started doing this stuff in the 70s, early 70s, memory and CPU were equally matched. In a single instruction cycle, we could do two memory accesses, one for the instruction, one for the data. Worked perfectly. Over the intervening time, memory got 10 times faster. That's a logarithmic scale on the y-axis. Memory got 10 times faster, little bit more. CPUs got 3,000 times faster, hence that huge gap off on the right, about a factor of 300 times. So yeah, we got to hide memory latency. The memory is slow. So what does all this tell us? It says that RAM is not really random access memory anymore. It's not true that all locations take the same amount of time to access. It depends on where you're accessing them and how recently adjacent locations have been accessed, pulling the thing you want into the cache. Wouldn't it be cool if your program could give a hint to the CPU to say, hey, CPU, in a few instructions from now, I'm going to need this location, so why don't you start fetching it now? A prefetch instruction. You can do that, but Python can't allow you to express that, and C does not allow you to express that either. There are a bunch of instructions like that that the machine has, but our languages do not let us get to. So we're giving up a lot of performance that the hardware can actually provide. The lesson from this first line here is, go ahead and use memory, just don't read it or write it. In particular, avoid random reads. Go sequentially, because RAM is kind of like disk now. Random reads are 10 times slower than sequential reads. And try to avoid writes. When you do an occasional write here or there, that's fine. The chip has a special buffer called a write buffer to hide the fact that writes are very slow. But if you do large vector writes, the write buffer fills up, and after it fills up, which occurs very quickly, it's a small buffer, then all succeeding writes will run at memory speed, and your CPU slows to a crawl. Access vectors in blocks that are L1 cache friendly. You really need to start thinking of your program not as having access to a giant array of RAM, because it's so slow, but really in terms of having access to the L1 cache. If your work doesn't fit in the L1 cache, performance is going to go down the drain. You're going to be running at L2 speed or L3 speed or worse, RAM speed. Try to use hardware primitives, which is why we use NumPy, instead of these beautiful fuzzballs that we get from Python, where, how big is an int now? It's 80 bytes for an int, something like that. They provide all sorts of wonderful services to us, but for high-performance computing, we can't afford the overhead. The machine has high-speed instructions for its primitives. We need to stick with the primitives so those instructions can be used. Write code, usually in C, that takes advantage of knowledge of the out-of-order execution and the nature of the cache versus RAM. And touch the big data once only. It's a big win because memory overhead is such a problem. Another lesson is that speed has value. For a project that I cannot describe in any depth, we think, about $300,000 a month on servers. If we could speed up that code not by 100,000 or 10,000 or 1,000, but just by a factor of 100, we would free up $297,000 a month. That would pay for a lot of programmers or a lot of additional game developers, or if I got 10% of it, I could afford long pants. So if we start thinking about performance as something that we're responsible for, instead of just saying to the operations team, oh, add more servers and the problem will go away because our stuff is horizontally scalable, we'd lower our capital expenditures, our operating expenditures. We'd also lower our CO2 emissions, so maybe New York would not have to drown in the next storm. If that's funny, you weren't watching TV. I have friends who live there, and it was not very pleasant for them. Another lesson, clusters are hard. Anybody remember that old Barbie with the pull string? You pull it and she says, math is hard. Well, clusters are hard. Over on the left is a cell phone snapshot of a piece of paper attached to the whiteboard in my group, Business Intelligence, with the 5 prime directives for BI. Captain Picard got by with 1, we have 5. And off on the left, for each one of those 5 prime directives, an example of where we failed to meet that directive because clusters are hard. I'm not going to go into details. You can read the slide as well as I can and send me an email if something's not clear. The point is, we don't know how to make this stuff work very well. Batching. Why are we still doing batching? I love this picture. I use it in every slideshow, so the reason I'm using it here is to beat on batching, but really, even if I had no reason, I'd still show you this great photo. You can sort of see the pig standing out in front of the python. One of them is involved, one of them is committed. Thank you. 2 shows nightly, bring your friends, tip your waitress. When you do batch programming, jobs might fail, and they might fail silently, in which case you find out when you come in the morning and your customers or clients have sent you emails saying, where's my data? Or they might fail loudly, and then you get a 3 a.m. phone call. In my case, it was a 5 a.m. phone call. And my boss actually wanted me to call other people on the team and wake them up at 5 o'clock in the morning. And I said, no, not unless you pay me like a manager. That's what managers get paid for. I got that phone call because we happened to have one of our guys in China visiting his significant other, and he happened to be monitoring our system because what else would you do when you're in China visiting your significant other? So he called me to tell me there was a problem with the batch job. Don't like those late night phone calls. And If you're doing classical batch processing, which starts at midnight and runs until 8 a.m. or so, you've just given up a lot of your compute time, so you're going to have more servers to get the work done in the length of the batch window. And of course, batch jobs add latency. You submit a request, and at some point in the future, you get a response, by which time you've forgotten what the question was. Batch jobs are 1970s technology. We should not be doing them. So fast code is cheap code. Save money, save the planet. Your machine is insanely fast. The computer that I'm using at my employer gives me 80 billion instructions a second before hyperthreading. Add in hyperthreading, it's probably about 100 billion instructions a second. How many instructions do you think it takes to move 140 bytes from my cell phone to your cell phone? Do you think you could do a lot of those messages per second if you had 100 billion of them, 100 billion instructions per second to do? I kind of think you could. Or you could scale it out, as Twitter has done. The Twitter cluster, according to the guy in charge of the group that keeps their servers running, I talked to him a few weeks ago, their cluster is 100,000 plus servers. Now, sure, not all of them are moving messages from point A to point B. Maybe it's just 1%. Maybe it's just 1,000 machines. I wrote the same code in 2008. It conformed to the Twitter API. It handled the 2008 volume on one box. Not 1,000, certainly not 100,000. Last week after the election, anybody here, you know we had an election, right? Yeah. Twitter put out a blog post, a press release disguised as a blog post, boasting that their system had not crashed on election night. That's kind of like a car company putting out a press release saying, our cars do not explode when driven on roads by people. The fact that they put out that blog post tells you how close to the hairy edge they are of falling over. Because they're moving 140 bytes from my cell phone to your cell phone, and that's a hard problem. Makes them get all scrunchy inside. Speed up your code first. If I can write code in a week's work to handle the Twitter message volume conforming to their APIs on one box, so can they. Clusterize is a last resort when everything else has failed, because clusterizing introduces so many problems you don't want to deal with. If your business is real-time, your software should be too. Batch mode is convenient for programmers, but it produces lousy results for our clients because it introduces latency. It means we have to use more servers to make up for the limitations of the batch window, and it makes things fail when we're asleep. Online code fails when we're awake. That's a better time to fail. And make sure your tools are working correctly. Remember that problem we had with NumPy on my slides earlier on, where NumPy was being passed a mixture of string, float, and int, and therefore it couldn't do a good job? So we have all these wonderful tools, make sure they work correctly. Another example of that in our case is this piece of crap database. We've put all sorts of tables in it over the year. We've never optimized it. And I've worked, as I said, at other database companies with the same problem. The database gives you all sorts of ways to optimize your stuff, and they're too hard to understand. It's kind of like you're put in a garden with 100 paths in front of you, and at the end of one path is a gorgeous prince or princess, or possibly the Shellyak corporate entity if you're into that kind of thing. Star Trek reference. How many people got it? One hand went up. Okay, I'll see you later. And at the end of the other 99 paths are tigers that are going to bite your face off, and you can't tell which is which. So we have this database. We haven't tuned it. Of course, the performance is garbage. Make sure if you're using sharp tools that you're using them correctly and not just using them to pound dirt. One more thing. Hey, I'm going to end on time. One more thing. I've been doing this, as I said, for quite a while. And one unrelenting theme over the 40 years I've been doing this, I fell in love with this stuff when I was 13. A friend of mine showed me how to mark up optical mark cards. They're kind of like the old punch cards, but number 2 pencil. You mark them up in the cafeteria, and I was hooked. And by the end of the week, I knew what I was going to do for the rest of my life. I'm very lucky that way. Back in the 1970s, we had computers in our junior high school because one of the teachers wanted to do that, and she was married to the mayor. They tried to cancel that program after a year, and I went to the Board of Education. And I was like 14 or something, and I said, at the public testimony, I said, you should provide money for this, and I gave them a list of bad reasons, and they did. And afterwards, I asked one of the board members, I said, I'm only 14, but I'm not stupid. My arguments were terrible. Why did you give me the money? And the guy said, we cut the budgets of dozens of programs, and no one cared to show up but you, so you got the slush fund. Okay, if you don't ask, you won't get. So for 40 years, we have been coming up with better languages, better operating environments, better tools. And in the late 90s, we took a turn, a bad turn. It was the dot-com boom, and we were very concerned with making websites that wouldn't fall over if they got very popular. I don't know if anybody here remembers that eBay fell over a lot when it got popular early on. So the industry consensus became, programmers don't worry about productivity, about performance, just worry about horizontal scalability, and then we can throw the performance problem over the wall into ops. And they can improve performance by just adding machines. Scale it up. Scalability is the solution. But here's the thing. As programmers, we have dozens of tools in our toolbox for performance. I've shown you a few tonight. All we gave the ops team was one tool: add more computers. What's the result? The result is Twitter has over 100,000 servers in its data centers, and that's just insane. They're not the only ones. Google's building huge data centers. Facebook, Apple, Microsoft, lots of other companies, including some I can't talk about, are building data centers. The New York Times was running an article a couple months ago about how data centers now use a significant fraction of our nation's power, which means we're burning coal or oil to power these things. You know what happens when you burn coal? Every time you turn on a new coal power plant, you condemn a couple hundred children in the world to die from asthma. We should not do that. I say this because I used to work at a company that did high-efficiency lighting, and that was part of the argument that I made there. We don't really want to be burning coal. We don't want to be building data centers, and yet our data centers are filled with racks of servers. We're running out of power, we're running out of chilling capacity, we're running out of physical space. We should not be doing this. Efficient code is a competitive advantage, and as programmers, we should take back from the ops team the responsibility that is rightfully ours to write high-performance code. To do that, we cannot have people in the situation that I was for the speed-ups I talked about tonight. You should not have to know this low-level, mind-numbing detail about computers. I like this, but I have no social life. Never have. Tried it once. Didn't like it. Ugly bags of mostly water, as far as I can tell. Anybody get that joke?
Star Trek.
Thank you. Which series? Thank you. My boss, the one I was making fun of before, he said he saw Star Trek, and I said, "Oh, what do you think? What do you like about it?" He said, "Oh, I love Star Trek with Captain Picard." That's not. You mean there was another series before that? We need to take back the stuff that we know how to do well, that we have the tools to do, but we need better tools to do that. And one tool in particular that I would like to see in Python is a high-performance numeric vector class. So that if you give Python an expression that says y equal ax cubed plus bx squared plus cx plus d, it would know how to do that efficiently using the underlying vector instructions, knowing how to block things in the cache, knowing how to schedule things as efficiently as possible on the machine in question. It could do the stuff that I had to do by hand. Now you might say, why a numeric vector class? Why not a generic vector class? And the reason is the underlying machine doesn't know from generic. It knows about numbers. Intel and AMD and IBM and ARM have added the vector instructions because those are the things that clients need to do a lot of on computers. We have huge amounts of data flowing into our systems now, whether it's sensor networks or social networks, massive amounts of data coming in. It's going to be processed in vector form. The hardware can support the vectors, but our languages aren't up to the task. So if you want to get the kind of performance I got here, either spend 40 years like I did learning this nonsense and making fun of database companies and Twitter, especially. It's easy to do Twitter. Or let's press the language vendors, in particular Python, because it is such a marvelous language for everything else, to give us the tools we need to take advantage of the underlying hardware, this 100 billion instruction per second machine that you can get off the shelf, not fancy hardware. If you need more compute, by the way, you can get an 8-socket motherboard and double your compute power. If you need memory, you can get 2 terabyte machines off the shelf, not fancy stuff. If you go beyond that, yeah, then you're going to get reamed. But 2 terabytes and 100 billion instructions per second, that's a fair chunk of compute power. Let's find ways to make use of that effectively instead of trying to scale out and fill up our data centers with rack upon rack of cheap boxes.
Thank you so much, David.
You're welcome.
For a
My pleasure. Thank you for the opportunity.